to show how two first-order processes in series can lead to a second-order transfer function. We'll use the example here where we have two well-insulated tanks in series, where the flow rates entering and exiting the tanks are going to be constants and the same. Here our goal is to determine the transfer function that relates our output variable, which is the outlet temperature of the second tank, T3, and we'll evaluate this in deviation variables, over the input to the first tank, which can vary, T1. So in order to do this analysis, we need to conduct two energy balances. Why? Because from our first balance, we'll be able to get T3 as a function of T2. So tank 2 will allow us to find T3 as a function of T2. However, because our goal is to find T3 as a function of T1, the second tank balance is insufficient. Why? Because T2 is a function of T1, and we can find this relationship by the energy balance on the first tank. So in this case here, we have no chemical reaction happening, and the system is well insulated, so therefore our energy balance for both tanks can be simply written down as the accumulation of energy is equal to the energy in minus the energy out. And for tank 1, the accumulation will be d energy dt, and that will equal the inlet energy, which we can find via the enthalpy multiplied by the mass. So we have a mass flow rate of F coming in, multiplied by enthalpy. In this case, will be Cp multiplied by the temperature T1 minus a reference temperature. We'll subtract that from the out term, which will be the flow rate coming out, F, multiplied by the enthalpy there, which we'll say is Cp times T2 minus Tref. We'll do some analysis here where we have the energy inside the tank can be represented as the mass of the fluid, which is going to be V1, which is a volume, multiplied by rho, multiplied by the enthalpy, which will be Cp. Here, because we're assuming the fact that the tanks are well mixed, that means that the temperature of the outlet is going to be the same as the temperature of the fluid inside the tank. So we can write this as T2 minus Tref. And what we can also do on the right-hand side is the Tref terms will cancel out, and that leaves us with FCP times T1 minus T2. We can simplify this a little bit more by factoring out the constants, which in this case would be the volume of the fluid inside the tank, rho, and the heat capacity. And we can also take advantage of the fact that since T reference, or reference temperature, is a constant, its derivative will be 0. So therefore, when we finish this up, our balance on tank 1 will be V1 rho Cp dt2 dt equals FCP times T1 minus T2. And one final simplification we can take advantage of here is the fact that the heat capacities will cancel. For tank 2, we have an identical energy balance, with the only exception that the subscripts for the temperatures are different and for the volume are different. Our next step will put this into deviation variables. We have our variables here are T1 prime, T2 prime, and T3 prime. Fortunately, all of our terms are linear. So therefore, in order to put these equations into deviation variables, all we have to do is add primes to these respective variables. Note, there are no primes necessary for F, V, or rho because they're all assumed to be constant in this question. What we can now do is develop the transfer function for both tanks. We've shown that on the screen here, but an important point that we want to do here is we want to put things into standard form. So when we put things into standard form, what that means is the T2 prime here and the T3 prime here, the coefficient in front of them must be 1. This can be done by dividing everything by F. And when we do that, we end up with the equations that you can see right here. And then in the next step, what we can do is we can factor out the T2 prime from the tank 1 equation and the T3 prime from the tank 3 equation. When we complete this, we can develop our transfer function. So for tank 1, we'll have that T2 over T1 prime equals 1 over V1 rho over Fs plus 1. And similarly, for tank 2, we have that T3 prime over T2 prime equals 1 over V2 rho over F s plus 1. Although we have found these two transfer functions, our overall goal, recall, was to find t3 prime over t1 prime. And there are two ways that we can do this. One way we could have done it was substituted in t2 prime from this first equation and substituted it in to the second equation. Another way we can do this is also recognize the fact that t3 prime over t1 prime is just going to be equivalent to doing t3 prime divided by t2 prime multiplied by t2 prime over t1 prime, with the t2's canceling out. Either way will get you to the same place. So when we do this, we can see the fact that t3 prime over t1 prime equals 1 divided by v1 row over f s plus 1 multiplied by v2 row over f times s plus 1. And what you'll notice here is the fact that we don't have to factor this out, but we now have an s squared term in the denominator, which means that we have a second order transfer function. So this shows the fact that although many chemical processes do not have second order dynamics naturally, if you put multiple processes together in a control scheme, which can happen, so we can develop transfer functions that are second order in spite of the fact that each of the individual processes is first order.